And now I'm going to introduce Dr. Stu Waterman, who has been my partner in science and one of my best friends for 35 years. He's the CTO of the Climate Adaptation Center, and I think he's one of the smartest guys I've ever met. And I mean that. And he's going to talk about the other part of the triple threat, and then I promise, we're shifting gears to solutions. Oh, okay, right after the break. Thank you again. And now I want to introduce Dr. Stu Waterman. Stu has been my partner in so many things. We met years ago when I started working at the National Center for Atmospheric Research, and Stu worked for a Canadian company. And little did I know, but a few years later, I was going to be working for that company too. So Stu he's an atmospheric scientist, but more than that, he's like the engineer scientist. He likes to get things done. We've built ground stations all over the world to bring down satellite data, whether it be from weather satellites or Earth environmental satellites or from digital globe high precision satellites. And Stu has been in this business for as long as I have been. So, and we don't want to count how many years that is together because it's obscene. But he's going to talk about the excessive precipitation, and we'll talk more about the Hurricane Ian excessive precipitation. But there's two kinds of precipitation that are excessive, right? Too much or too little. And so, live from Las Vegas, Stu Waterman.
Thanks, Bob. Bob mentioned I'm the Chief Technology Officer for the CAC. Well, that really means that I'm the Chief Technology Officer. That really means that I'm the Chief Nerd. And like nerds everywhere, I tend to over-explain things, so there's going to be too many slides, but I'll go through them anyway. And rest assured, they'll all be on the website. They'll all be on our YouTube channel. You'll be able to review them at your pleasure. So at the bottom of everything here is the fact that the world is warming. And you've seen this chart before. You've seen lots of them. The key thing, though, is that what we're doing now is going beyond history. So meteorology is all based on what's happened before and how often it happened and what happened when the event was over. Sorry. There we go. So what we're looking at now is temperature around the world that we're not familiar with and that meteorology hasn't studied because it hasn't been there. So not only is the world warming, but the United States is warming. And the interesting thing is that 70% of the world is covered by water. So when you look at the average warming temperature, you're looking at mostly the ocean. And if you look at the land where you happen to live, it's warming a lot faster than you've been led to believe. And so in the States, we're up by 1.7 degrees Celsius instead of just 1.2. And every degree matters, every tenth of a degree matters. And if you look at number of possible futures that we're generating for ourselves, the colored lines up here. I mean, the green one is the absurdly optimistic one. The yellow one is the one that we're committed to right now. We could disagree on where we're going to end up at 2100, but whoops, bear with me. But when we're getting in around 2040, they're all about the same. So a lot of this is to a certain extent baked in, and temperatures are going to get at least that warm before we can do anything about it. Now, the other thing is that 70% of the world that's covered with oceans is also warming, and most of global warming is going into the ocean. 90% of it is going towards warming the ocean. And as Bob is quite fond of saying, you know, the hurricanes are fueled by warm water. And the warmer the water gets, the more fuel you have. And we're busily filling the gas tank of future storms by warming the oceans. So looking at precipitation, the key thing is that warmer climates are wetter climates. And the reason for that is that it's just a simple bit of physics that we've known for centuries, but hadn't really thought about too much. Warmer air holds more water. It evaporates more water from the earth or from the ocean, and it can hang on to it before it dumps it. So about 7% of precipitation intensity we increase precipitation intensity about 7% per degree of Celsius of warming. But the other thing is that, but total precipitation increases a great deal more. And we saw that with Ian, for example. I mean, the storm is large, it holds a lot of water, and then drops it. How fast it drops is the intensity, how much it drops is the total precipitation. Now, we mentioned a little bit about meteorological history when I was looking at the temperature chart. Well, if you look at not just temperature, but also precipitation, so climate, we got an average, right? So we say, well, you know, it gets a little bit colder in the winter, it gets a little bit warmer in the summer, and on average, it's okay. And then, sure, there's some extremes, you know, we could get a really cold winter here, or you can get a really hot summer. But they don't happen that often, so we don't worry about it too much. So what we've done, what meteorologists have done, and what civil engineers have done with the results of the meteorological history, is we said, well, okay, we're gonna plan for the average, because that's where we are most of the time. And we'll provide for the extremes to the extent that we can afford to. And we say, well, okay, we could probably provide for that. But out here, it's so rare that we probably won't. It's not really economical to provide for it. It would cost a lot of money, and in the meantime, we probably will have changed housing structures anyway. So we draw a line somewhere and build to that. Well, the problem is that the climate isn't what we would call stationary. The climate's non-stationary, it's moving. And we're warming it, so we're changing the average. Well, obviously, you know, a degree here and there, like Bob said, isn't really going to make much of an impact to us as individuals. But the key thing isn't the average, it's the extremes. And we're talking about extreme precipitation. Well, all we've done is move the average a little bit, but all of a sudden, out at the extreme end, these were events that were impossible before we moved the average. So we moved the average a little bit, and we've introduced these extreme events that we've never seen before. And at the other end, their cold events are disappearing. We have warmer winters now. The winters are actually warming faster than the summers. And so this is not important here, but where I used to live in Colorado, losing the cold, having warmer winters is just not a good thing because you can't ski so much. So the other thing is that warming's not evenly distributed. And of particular interest to us, we're looking at, if you look at this map of where the 2022 temperatures were, it was the 5th hottest year on record for the globe as a whole. But if you look at where it was hot, interestingly enough, the Gulf of Mexico and the east coast of Florida were the warmest year on records in the ocean. And in fact, most of the warming that happened last year was in the ocean, the most intense warming anyway. The Pacific, we had the heat waves in Europe and in South Asia, rather. And so, you know, really it's a matter of where the energy is. All of this heating is really transfer of energy. We're putting energy into the Earth system, and then the Earth's going to do something with it. And it heats the ocean, that fuels the hurricanes. All of this is a consequence. Now, the other thing we found out recently is that, well, you think back to that graph where the tail was the extreme events that we hadn't seen before. Well, there are lots of extreme events that we have seen before, but just not very often. So we've taken a look at those events, and sure enough, over recent time, since 1960, we can see that, well, these things are happening more often. This is going to be a problem in the long term. Not only are they happening more often, but they're dumping much more water. Here we are, well, we're roughly in here, between 1 and 1.5. And we're already at about 8% higher precipitation intensity in storms as it is. And it will get progressively higher as the temperature warms. This is all, you know, it's not a random event. This is just a guaranteed outcome. So let's take a look at Hurricane Ian. And I was asked to talk about inland flooding and extreme precipitation. Well, so let's take a look at Orlando. We've talked about Fort Myers already, that tragic event, but now let's take a look at Orlando. If you look at the 2022 for Orlando as a whole, 20% wetter and almost 2.5 degrees warmer as an average. So if you take it month by month, you find that, well, there's Ian. Up until that point, Orlando was having a pretty average year, and then Ian hit. So 22 inches, 22.5 inches in Orlando, it was 24 inches at Fort Myers. It's a tremendous amount, it's a record for the month. And this happened. So you think about why flooding happens, inland flooding happens. So the water is falling on the surface of the earth and it gets absorbed. It's like a sponge. Fill it up. If it falls so fast that the sponge can't absorb it, then the water starts running off the surface. If you've got rivers, they take it away. And if the rivers can't keep up, then flooding happens. So in Orange County, hundreds of millions of dollars worth of flooding happened. And the thing that struck me, I hadn't realized, and when I know we're talking about insurance later, were these numbers. Hardly anyone had flood insurance. And the other number that was a little depressing was that 35% of the part of Orlando, or of Orange County rather, that flooded, those homes weren't in the FEMA flood zone. And listen, I'm not, giving FEMA a hard time. They do a tremendous job. But this is the problem of historic meteorology. The FEMA flood zone is based on the history of flooding and a little bit of a projection about how often it might happen. So if you've only got out-of-date information to work with to make your projection, then your projection's going to be wrong some of the time. And that's what happened to FEMA. It's not that they don't do a good job, it's just that they weren't able to consider a non-stationary climate. The climate is moving out from underneath them. 75% of presidential disaster declarations, and we've had quite a few this year, are associated with flooding events. And as I mentioned, in Orlando, basically we're looking at soggy ground that was already wet. We got intense rain from as Ian passed over. It's flat terrain, as one of the managers of infrastructure for water control in Orlando said there was just nowhere for the water to go. And all of their flood control efforts, the lakes, the retention ponds, everything filled almost instantly and overflowed. And Orlando was underwater. And this is really what it comes down to. 20th century planning and design standards just aren't going to be adequate in the 21st century. We've got to find a way of migrating our planning into a future which isn't the same as the past. Here's the rest of the United States. In just actually 5 weeks, they had 5 1,000-year rain events. Now, a 1,000-year rain event is something that's happened so seldom that the odds of it happening are basically 1,000 to 1. And we had 6 of them in the year, in the 2 months, and 5 of them happened just in 5 weeks. And these floods and rain events were everywhere, including one of the 5 was in Death Valley, which is pretty much the driest place I can think of in the continental United States. Flood forecasting is possible, but it's very difficult. I did not know, well, until recently, we didn't have a National Water Center, but we do now. It's part of NOAA. And they did produce a flood forecast for Ian. This is after it had made landfall, but before it crossed Central Florida. And sure enough, they said, yeah, we're going to have major flood in several locations in Central Florida. Fine, catastrophic flooding, they got that right too. But this is like one or two days before the flooding happened. There's not a whole lot you can do at that point. But these resources do exist, and they are available to you. If we have another, hopefully not recently, or not soon, but if we have another event like Ian, there is somewhere you can go to find out what's going to happen or what they think will happen. And this was all actually quite accurate, particularly obviously the first, this crosshatched section is the 1 to 3 day forecast. So they didn't have too far to predict, and they got it right. But the resources are available. Let's take a look at a different kind of rain, different kind of extreme precipitation event. There's a phenomenon called an atmospheric river, which is it's a very sort of poetic way of looking at meteorology, but these are basically rivers in the sky. They're long, narrow bands of intense water vapor transport. And they move a ton, well, many tons of water. An atmospheric river can move 15 to 17 times, or sorry, 7 to 15 times the amount of water the Mississippi River moves. And they're just absolutely massive. Thousands of kilometers long, 300 kilometers wide, 300 miles wide, rather. I like to think about tropical storms like Ian as a sort of tank truck of precipitation. Truck drives up, open the valves, a lot of water dumps out, and then the truck drives off and everything dries out. The atmospheric rivers are a pipeline. I mean, they keep pumping water, and storms move along the atmospheric river. And every time the storm moves along the atmospheric river, it picks up more water, hits the ground, makes landfall rather, and dumps. And this happened quite a bit in California in December and January. And we'll get to that in a second. But atmospheric rivers are important. We need them. About 50% of the annual runoff for a lot of the United States coastline and for places all over the world depend on atmospheric rivers to provide the necessary precipitation for agriculture and everything else. So they're beneficial until they're not. And it turns out that in December and January they weren't. So here's what they look like. This is, I won't go into the details here, but this is like the low pressure zones that you see on your TV weather forecast. So there's the low pressure area. Here's the cold front. Here's the warm front. The usual stuff. So what happens with the atmospheric river is that the cold front pushes into the warm, moist air here and compresses it basically, and the winds start going along the margin of the cold front and start pumping the water along with them. This is what happened when that phenomenon was inflicted upon Pakistan this year. They already had been having a minor flood because global warming had accelerated the melting of glaciers in the mountains that form the source for the Indus River. And so they were already getting, the river was already full. It's the monsoon season, so the ground was already wet. And then they had 15 days of extreme precipitation courtesy of an atmospheric river. And it devastated the country. 33 million people were displaced by the storm. I was reading this morning that 8 million of them are still without a home afterwards. Total damage, $30 billion between physical damage and economic loss. It's just an incredible event. And that's what it looked like. Pretty much like that low pressure diagram that just showed. This is it. It basically sucked water out of the Arabian Sea and dumped it in Pakistan. This is what it looked like from the satellite view. This is beforehand. It's the Indus River that comes right down through here. The melting glaciers are up here. The river was already pretty much full. Then we had the 15 days of rain, and look, water is everywhere. And months later, it's still there. We get them too, we being the United States. The whole West Coast basically depends on atmospheric rivers for their, their annual precipitation. California in particular, even though they've had a historic drought, 50% of their rain that comes from atmospheric rivers. So they were a little bit impoverished from atmospheric rivers for a while. And then December and January happened, and hydrologic whiplash. That's what they call it in California. It's basically you go from too little water to too much water. Hardly any in between. And this has been an ongoing problem in California since the 1800s. 1938, an atmospheric river storm did this to Los Angeles. I guess school was out. So that's just a 1 in 50 year event. That means it has a 2% chance of happening twice every century, more or less. So the government decided, well, we can't have this happen again. So they fired up the Army Corps of Engineers, and they spent 20 years and a ton of money making sure that this wouldn't happen again, or they hope. Then what their solution was what they called channelizing the Los Angeles River into the thing that we've seen in movies, from the Terminator to Grease, to any number of car races have happened, of car scenes have happened in the Los Angeles River, because it hardly ever has any water in it. So they channelized it, the whole idea being that, well, we can't control the water coming in, so the best thing we can do is get rid of it as fast as possible. So they streamlined the river, basically, and then built all these Art Deco bridges across it and everything else that we've come to know. And this is what happens when an atmospheric river hits. That whole deep channel fills with water. That's Griffith Park in the background for anybody who's an ex-Angelino. And because the whole thing about channelizing to get rid of it as fast as possible, this water goes up to 45 miles an hour. So it's really ripping, which is fine as far as it goes, but if we just get that little bit too much water for the Los Angeles River, that 45 mile an hour flood is going to spread. So this is what an atmospheric river looks like in action. This was in December. And so this is a satellite image of moisture in the atmosphere. This orange band down here towards the tropics, that's a high moisture area. This is what an atmospheric river looks like. This is Hawaii here, and this would be the Pineapple Express that you hear about. And this is what happens. This is Capitola, a small coastal community in Santa Cruz County. This is San Francisco. And this all happened in just almost a matter of hours. So what happens with the atmospheric river is you've got a ton of water. The atmospheric river runs right along the surface of the ocean in the bottom 1,500 feet of the atmosphere. And it comes on shore and it gets forced up. And as you force the air up, it gets cooler. When it gets cooler, it can't hold as much water, so it starts to rain. And the higher you force it, the more it's going to rain. So in California, it hits the coast, it starts dumping, and then it climbs inland to the Sierra Nevada mountains, and it really dumps. And that's exactly what happened here. When it gets to the Sierra Nevada mountains, hopefully, from a California point of view, it turns into snow. And they actually count on the snowpack being a sort of natural reservoir for water for the rest of the year. Well, the climate's warmer now, and the snow line is a lot higher than it used to be. So areas that used to get snow that would just sit there, now they got dumped on with a ton of water, and it ran down the mountainside and into the rivers and flooded everywhere. And this is the result in In 23 days, they went from extreme drought to extreme precipitation and flooding. These roughly white areas here, those are 20 feet of snow in the Sierra Nevadas that wasn't there before. And everybody goes, well, that must be okay, because that means that it's too bad about the flooding part, but this means that we're probably out of the drought, right? Well, we'll talk about that in a second. But this is what I was talking, whoops, wrong button. So this is what I was talking about. We've got the precipitation event. It's not only is it more extreme, but it changes its makeup. The percentage of rain versus snow is changing, so there's more rain and less snow. So that means less natural water storage and more flooding, all at the same time. So it's a double whammy, really. And the other thing about, this particular storm, or series of storms really, in December and January was certainly damaging. But what it got people thinking, well, what if we had a really bad one? What would that look like? Well, there have been really bad ones in the past. There was one which in California is known as the Great Flood in 1862. Now, hardly anybody lived in California in 1862, so it was a disaster, but it was a relatively small disaster. But we've already doubled the probability of these extreme events. And that was a 1 in 200 year event. Well, that means that if we've doubled that likelihood, that means it's now a 1 in 100 year event. So people start asking, well, is this the big one? Are we going to have is the big one not, maybe we're worried about the wrong big one. The big one's usually thought of as the earthquake that's going to level California, but maybe really what we have to worry about is California washing out to sea. Infrastructure is not designed for what they're calling a megastorm. If the big one happens as an atmospheric river event, the estimated property damage now that California has built up is almost $1 trillion. $400 billion of property damage, $325 billion of economic loss. It will be a disaster of enormous scope. And so we're starting to look at, well, how likely is this to happen? Can we can we figure this out from modeling future global warming? Well, it turns out that we can. And if you look at 1.5 degrees of global warming, which is, we're almost there. We'll hit 1.5 degrees of warming in the next, well, this decade, I think. And that's already going to take, these are, the way to read this column is that this is a 1% event. So 1 in 100 is another way of saying it. So 2 in 100, this is the 1 in 50 year flood that we were talking about before. So that, if we look at this line, the projection for the 50-year flood event, well, it turns out that it'll be, more like a 27-year event by the time we get to 1.5. So later this decade, the 1 in 50, what used to be a 1 in 50 year event is now going to be a 1 in 27, 28 year event, and so on. And then as we get to the likely outcome further down this century, we're going to be taking them down to 1 in 25 year events, or it's going to be, a 1 in 16 year event, and we're just simply not ready for it. We haven't planned for it. We don't know what we're going to do with it. And to make it even worse, it's not going to solve the drought problem, because it turns out that climate change is sneaking in the back door on the drought side by drying everything out. So water withdrawals is the way, how much water the society is going to need. Without climate change, we were already looking at increased demand for water. With climate change, that we're looking for up to 50% more water by 2060. And Florida is right in there. So I didn't spend much time on drought, but I'd love to entertain questions about extreme precipitation.
Mandatory elevation in Sarasota, Manatee County, all the maps lowered that base flood elevation or design flood elevation. I'm just curious to why that is. I know Manatee adopted the new maps. I'm not sure Sarasota has yet. But I just was, you know, it seems counterintuitive, that's
Yeah.
all.
Well, the thing about FEMA flood maps is that they're really based on, as I understand it, they're based on river flooding, or flooding out of a channel, overflow, if you like. Not so much the kind of flooding that we saw in Orlando. That was one of the reasons why Orlando was why so many places were damaged outside the flood zone, the FEMA flood zone, because FEMA looks at rivers rising and eventually cresting over the bank and flooding the associated floodplain. So extreme precipitation events, there is no, everywhere is a floodplain, basically. I'm not familiar with the Sarasota maps in particular. I know FEMA is constantly trying to catch up to reality and fine tune its maps. And I mean, they're doing as good a job as they can, but they're pretty slow. Although on Longboat Key, I imagine they're looking at like storm surge flooding and that sort of thing, right? So it's a different kind of event. Oh, sorry. Yeah.
Yes, Stu. Great presentation, by the way. One of the ways that droughts break in California, which has happened for hundreds of years, is during El Nino phenomena, warm ocean currents in the Pacific off Peru. But because of climate change, the oceans have been warming, 70–80% of the oceans. So to create equilibrium, what happens, we have upwelling in the Pacific, cool ocean currents off the coast of Peru, and La Nina is lasting longer, and there's been a high correlation in this multi-level drought. Partly is because of this 3-year La Nina, which has never happened before. So my point is, in the long run, less El Ninos, more La Nina phenomenons, I agree with your points, will not really alleviate droughts in California for very long.
Yes, exactly. Well, and we're in a transition year now as we go to the next El Nino event, and that things are going to get a whole lot warmer. We've had 3 cool years in a row, and when El Nino hits, then we're likely to set a new temperature record, and everything else will drive as well. Yeah.
Is there any way to assess the capacity of various is there any way to assess the capacity of the composition of the earth, the ground, to absorb water, and to somehow use metrics to be able to predict the amount of rainfall a particular area could absorb within a specific amount of time? Is there any science around that?
Well, yes and no. Yes, there is science around that, but the problem is that it's such a variable phenomenon, and small distances can be, you can go from a porous surface that will take in lots of water to another surface where it just runs off, and it so much depends on preceding events. Has it been dry? If it's dry, you think, well, that's great, it'll soak up lots of water. But if it gets really dry, then it's too dry, and the water just runs off. And I live in Nevada, and that's what happens. Everything's dry. That's why we had a huge flood in a 1,000-year flood event in Death Valley, because the little rain that fell, it was only about 4 or 5 inches, but it just ran off instantly. So it's a really, I was trying to get that across with the flood prediction map that I showed. It's an extraordinarily difficult thing to predict. I mean, the rainfall is hard enough to predict, but what happens to the rainfall on the ground is even worse. So I don't mean to depress you, but there's no quick answer to that one. Yep.
Stu, thank you so much. Let's give him a big thank you, Stu. Thank you.